Okay, now I'm going to tell you about partial derivatives, and this is the part where multivariable calculus really starts, because we're actually going to start doing calculus that is taking derivatives of functions of several variables. And so remember that when you have an ordinary function of one variable, then the graph looks like this, like a curve of the function, and then you would have the problem of finding the tangent line to a point on this graph, and then the slope, right? If this was a point x, and the slope would be f prime of x, right? And since you already have the slope and a point through the line, you can completely determine that line. But more, so that's like a geometric interpretation of what the derivative is supposed to be. More from a quantitative point of view, you can think of a derivative as a rate of change of f with respect to x. Okay. Now, what's going to happen next is that we now have a function of, say, two variables to begin with. And instead of trying to find a tangent line, as I mentioned on one of the previous videos, you can think of finding a tangent plane to a point on the graph. So, for example, here you have this graph, right? And then the tangent plane will be something like this, a plane that looks like this. So it varies from point to point. And so that begs the question of what will specify a tangent plane on to this point on the graph. Before, a tangent line is sort of specified by the slope, which you can think of as which just is like rise over run with respect to x. But now, so like the slope measures how much the line is tilted with respect to the x-axis. That's what I wanted to say. Now, for a plane, there are like two versions of being tilted. You can sort of be tilted with respect to the x-axis, right, like this. But you can also be tilted with respect to the y-axis, for example. And so that means that there are two versions of tiltedness, and those are being described by the partial derivatives. So there are like two slopes, if you want, which are the partial derivatives of f with respect to x and f with respect to y, and that's the notation that we will use in general. So this d has been turned into a curly d, which is known as the del, the letter del, the Greek letter del, I guess. So geometrically, how can you think of these derivatives? I will show you an animation at the end of this video, which will make things more clear. Let's say, suppose that this is the x-axis, this is the y-axis, this is the z-axis. Here you have z equals f of x, y. And so, what do I mean by the partial derivative with respect to x? What I mean is the following. Imagine that, say, you choose a point here, right? And so, what this means is that you're going to take the derivative with respect to x. So the notion of partial means that you're not considering every single variable as an actual variable. You sort of pretend that the other variables are constants. So if you take a partial derivative with respect to x, it means that the only true variable at the moment is x. So that's the only variable that you're allowed to change. So if you're only allowed to change x, that means that you have fixed y. So this value of y has been fixed. And then you can move along this line, because along this line, which is parallel to the x-axis, x is changing, but notice that y is fixed. And so the effect of that is that this line will lift. Like, imagine that you build a plane passing through this line, which is perpendicular to the xy plane. And so this gives you like a wall, an infinite wall, that somehow will cut the graph into a curve of stairs. Again, this will be more clear if you see the animation near the end. And then, with this curve of stairs, again, if you go look above this point, there will be some point here. And the slope of this, the tangent line to this curve passing through that point, will be the partial derivative of f with respect to x. So it's still like a slope. Similarly, you could now consider partial derivative with respect to y. That means that now you pretend that x is constant. If you pretend that x is constant, that means that this value of x is fixed. So now you're moving along a line that's parallel to the y-axis, because that's where y is changing. But again, you sort of think of this as creating an infinite plane which slices the graph into a curve. Okay? And now this one has its own tangent line. Okay? And the partial derivative with respect to of f with respect to y is the slope of that other tangent line. So they both have the same meaning. It's just that it depends which of the two variables you're changing. So in other words, what I'm trying to say is that the partial of f with respect to x is the rate of change of f when only x varies. And similarly, the partial derivative of f with respect to y is the rate of change of f when only y varies. Okay? So what I'm going to do now is show you an animation that explains this geometric picture more precisely, and then in the next video I'll tell you how to actually do computations. what you'll learn is that doing computations in this setup is essentially as difficult as it was on Calc 1 because you don't need new differentiation rules. So that's the good thing about this. So this is a nice concept of the idea behind a partial derivative. So as you can see here, you have the graph of some function which looks like this purple surface, and then the partial derivatives can be obtained in the following way. So we have this point P that you can see here that I'm moving around, and for let's say I choose the point P, and then what I do is say if I want to compute the partial derivative with respect to x, that means that x is free to change, but y is fixed. So I will move along this red line that you see here, which is parallel to the x-axis, and this red segment will lift to a curve on the surface, which is this red curve that you see here. And then this curve at this point P has some point above it, which is the point Q, and through this curve there will be now this looks like the graph. This cross section looks like the graph of an ordinary function, and then the partial derivative with respect to x is just the slope of the tangent line to this point. And a similar idea holds for the other partial derivative. So for the one with respect to y, now you move on a line parallel to the y-axis, which is this green curve, and this one will lift to a curve on the surface, this other green curve. And again, when you do the cross section, then there's a ordinary tangent line to this point, a tangent line to the curve passing through this point, and the slope of this tangent line is a partial derivative with respect to y.